So, here everyone. Before we start, a quick question. Did anybody here attended the NZITF conference? If you're able to see. Yeah, few. Yeah, last time in the introduction, as Jed mentioned that my co-presenter Gavin and I were entangled like a quantum particle for this particular presentation. But this time, my another quantum entangled person is in Wellington, so I'm here to present this is for the 25 minutes. So let's start. So our biggest question is quantum threats to cryptography. Should we be afraid? What do you guys say? Yeah, no response. So when I started this talk and researching about this stuff, I was in a state of that dog expression. But after I'm learning a lot and then did a lot of research on that, so I got understanding that not that afraid, but we will discuss in this presentation. So I'm Jagan Boda, or you guys can call me Jay. I'm a senior pen tester at Spark NZ. And I have 10 years of experience in IT security. And along with my passion for security and breaking stuff and the quantum, and nowadays we got a 5G and IoT stuff. Along with that, I do enjoy the archery. Just archery, not hunting. A lot of people ask. Yeah, if anybody wants me to connect after this talk and any constructive criticism, please give it to this LinkedIn profile. And this one is definitely not a phishing link. Everybody asked that one as well. So, quick disclaimer. The views and opinions are expressed in this presentation are mine and do not reflect any official policy or position of my employers. And cover up more. Yeah, I'm not a quantum physicist, so please don't ask the too deep technical or quantum physics questions. And also, crypto and quantum is a bit complicated subjects on their own way because it involves a lot of mathematics and other stuff. So today we will cover this as a high-level summary and to just focus on the key ideas. So I'll start with the agenda is we'll just try to understand what are the quantum potentially scary and why it is. And then we'll move on to the what type of cryptos are in an issue. And then we will understand a bit of quantum stuff, basics. And then we'll move on to the RSA algorithm vulnerabilities or weakness, we can call it, not a technical vulnerability actually. And then we'll show you I can say the failed demo. We'll see that on the real quantum computer. So, and then finally we will try to see what we can do at quantum level. Yeah, next one is, so why quantum computing is potentially scary? Yeah, because it has a potential to break the encryption which we rely on today, and which our classical computer takes millions of years, which is our supercomputers can take millions of years to break our encryptions, but it can be done within minutes in a few years away. So yeah, you can say that with few years, right? Why we need to worry about it now? So here the concept, we have a harvest now, decrypt later, or you can call it as a store now or decrypt later. What it does is the nation state or hackers like us, it do not require a quantum computer today. We just simply store our encrypted data or anybody's unencrypted data. And once the quantum computer is powerful enough, we can simply decrypt it. So if this look like a far-fetched scenario, consider these are the news. And absolutely, I'm not blaming any specific countries here. So these are the actual news we got it from. Yeah, so consider these are, if they had a quantum computer right now, so it will be devastating actually. So due to this issue, we have to move on, and because of this threat, a lot of people already working on it to how to prevent it. So let's see like what type of crypto is a problem at this point in time. We have a asymmetric and symmetric. These are the mainly using, and then hashing also included, but not in this particular top out of scope at this point in time. So mainly, these are the guys who created these quantum algorithms. Peter Shor, might you heard, and then Laos Gross. So especially the Shor is having the one of the biggest quantum algorithm. It can solve certain problems within a polynomial time, which means exponentially. So it directly threatens our the RSA and the Diffie-Hellman and then EC, almost most of the public key infrastructure, absolute. Once the quantum computer is readily available with the proper proper missions. But now is on the other hand, we have a grower algorithm, and that one is the speed of the brute force searches. It can weaken our symmetric algorithms like AES and other stuff. We no need to worry about it immediately, but we may need to increase our key sizes. There is one more interesting quantum algorithm, which is a BHT. It and Grover both can be have a issues with the hashing as well, SHA-256, but we are not covering much about into that. We'll only focus on which is immediate threat to. So have a look. This is the key cryptographic methods, and then so we'll start with the basic classic like a substitute and then polyalphabet. These are the served well in past, but they no longer useful now because of our quantum. Our classical computers can able to easily break those. Now we focus on the modern and modern, which is symmetric and asymmetric one, which is like a if you see, look at in the red, all these are absolute. Once the quantum computing is absolute. The other one, these are the symmetric one. We need to have a higher key size, as I mentioned in the previous slide. But there is no immediate danger for this, so we can manage for that. So what we can do that now? So already the organizations already moving towards to the post-quantum cryptography, or we can call it as a PQC. We will talk about this later on. Yeah. So before going to deep understanding, let's go through the what is actually quantum computer and then how it does look like and what are the key factors and key properties actually. Sorry. So just have a look this one. It's look like a science fiction movie, but it is an actual quantum computer, which is, you can say this is the IBM quantum computer. The wiring and then structure is designed to control the qubits or quantum particles. And it require very extremely low temperature, even colder than outer space. So as we know today, we have only the place which is outer than colder space is the quantum computer places. So now let's start. Anybody don't like the physics and maths? Most of the people are hackers, so I don't think so. Yeah. So let's start with a little basics. The physics is generally divided into two branches. One is the classical physics, one is the quantum physics. Classical physics is describes the like a motion and gravity, like everyday things we see across the world. And the quantum physics, on the other hand, it deals with the smallest particle in the world, our universe. So the center of the concept is called as a quanta. The quanta is the tiniest energy or matter. So these are the quantum computer uses these the quantum computer leverages these quantum mechanics concepts to perform the I mean too much calculations, so we can say that. And they have a couple of weird properties, I can say. When I mention weird, some of the stuff still scientists are not figuring out why it happens, but it is there. Like superposition, entanglement, interference. There are decoherence and a couple of more, but in this talk, we'll just stick with three. Yeah, so first one is the superposition. Superposition, simply in a code, we can say that quantum particle can exist multiple state at once simultaneously until we measure it. If you can look at in the GIF, it says that until we measure, it will be a collapse in either state, either 0 or 1. And if we can still, given a layman terminology, when we toss a coin in the state of an air, it's considered as a quantum superposition state. Next one, we have entanglement. Entanglement is like when we try to connect two quantum particles, like in our intro. You can take it apart from the different galaxy. Even if you try to measure one, you can able to, you can able to understand what is the state of that other one. So this is a weird one, actually. Finally, there is the interference. Interference is like the quantum algorithms uses this specific phenomena to using the quantum like a wave functions to minimize the errors and then find the right answers. Now let's go through the what is the quantum bit or qubit. Like our classical bit, it's like a quantum bit. It's a basic minimum information we can store in the quantum computer. And it can be a 0 or 1 at the same time, as I mentioned in the previous one. We normally describe this as in a Bloch sphere. So the qubit can be anywhere in the sphere. So that's what we call it as a superposition. So it can be represent anywhere in that until we measure it. That particular property gives us the extraordinary power to calculate the complex problems. So if anybody wants to build a quantum computer today, so there are a couple of different ways of qubits are available, superconducting and trapped ion and so on. Especially what you saw the previous image, the quantum computer from the IBM, they're using the first one, superconducting qubits. Next one. So, we will discuss about the logical gates. These are the important concepts to do the calculation on the quantum computer. First, we'll go through the classical logical gates. It's a simple like a and, or, and so on. Based on the truth table, we can say it's straightforward, nothing to learn much. But if I can compare with the same thing with the quantum one, you may see the different weird names actually. So Hadamard or maybe polyx and other stuff. What these are does is when we apply a quantum circuit with this particular logic gates, it can enable the quantum phenomena like a superposition or entanglement. I will put you one thing. If you apply the Hadamard gate into here in a circuit, it can the qubit can be in a superposition. So yeah, so that's the advantage of that. Yeah. Next one is try to understand the difference between our classical computer and considering as our missions, and then quantum computer, how it is works. So I try to give us a difference between like this, but what I can do is I'll try to explain using a simple example. Just consider these are the 4-bit passwords, and we can try to brute force it using the both. I'm oversimplifying here, so don't get me wrong here. So if you take a classical computer to brute force this particular one, you require, it can does, but it will does one by one until it's find the right answers as you see in the image. If I try to using the same technique on the quantum computer, as we know the superposition here, you require only the 4 qubits and into the superposition because it can be both at the same time. So you can do all the calculation on the quantum computer. However, we already provided to the quantum computer right answer and at the same time wrong answers. So here where the quantum algorithms come into the picture, like a Shor's algorithm or a Grover algorithms, and there are many. These uses the wave functions, wavelengths to figure out the right answers and then eliminate the wrong answers. So there is if we have more than 16 or I think 200 qubits or something, we can calculate entire universe, observable universe calculation. So if it is increases the size of the qubit, it can be it can increase. I think this is shorter one. Yeah, you can increase it. It will be exponential actually. I hope I understood. Next. Yeah. Yeah, I will show you a small demo. Using the same thing. I'll try to explain the RSA key generation, and then we'll try to find out what are the key weakness they found, and then how the quantum computer uses these techniques to reverse it or the crack it. So yeah, simple one, RSA key. We take the 2 prime numbers as a P and Q, and we can compute as a N. That's a N. If you notice, the N is in the both private key and public key. So, and then in that process, we calculate the D as our private key. So the whole, of course, in a real time, these numbers are, are much bigger than the numbers. However, the security comes from the RSA is, see how hard it is to getting back into back to the P and Q factors. If you take this classical computer or supercomputer, for one key, it will take millions of years with a proper 2048. We will go into the deeper Azure. But this particular concept can, using the Shor's algorithm, you can able to with this particular Shor's algorithm secured, you can able to find it faster. So I have oversimplified this, and don't get me wrong if any physicists are there. Uh, so there are a couple of steps to you can do that. First, we can able to create a superposition to explore all possibilities in the calculations. And then second one, we apply the quantum function to manipulate our data and then try to find the hidden patterns. And then once we send it to the quantum Fourier transforms, then it will discover the patterns actually. Finally, we can calculate the hour period. So next one in the demo, what I did is I took it the Shor's algorithm and then I modified a bit and then I tried to run on the real quantum computer, which is via cloud. Yeah, so you may think it's worked, but it didn't. But I've tried to attempt it as, so I just wanted to show you here. Yeah. On the left-hand side, you see this is the Microsoft Visual Studio, and the right-hand side is the browser. So I have connected through the IBM Quantum platform. Here my API keys, so please don't copy it. I think I already removed, I guess. Yeah. So before I start, what I did is I'm just taking simple F15 and I'm trying to I'm trying to find the prime factor for that. So normal kid might know that 3 and 5 are there, but I'll try to run it through the real quantum number and the simulator. So really didn't work. So I just run on the simulator, which is exactly run. We got it immediately. So I just wanted to make a point here is that, so this is a simple example, but in the future, the same thing will gonna happen. So that's what everyone is worrying about it and buzzing about it. So just start the video. It is not much. Yeah, it's not faster. Have a look. I'm still trying to get it right, but I had a chat with a couple of physicists in the US. But I think these exist in cloud systems. I don't know how reliable these are, so don't ask me. And the one more factor, you may see this Brisbane. So these are just they given the processor names, not actual quantum computer exists in the Brisbane. Yeah, I did executed my circuit on the real quantum computer, but I didn't get a proper response and then a right answer. So I just run it on the simulator. Yeah, you can get it very quickly, and then everyone knows the answer, I guess. Yeah. So this is what we got it from. Okay. Hope it liked. Yeah, so now we'll see this how realistic here to crack a 2048 hour we use every day. So you might see this a bit of two terms as a logical qubits and physical qubits. So currently existing physical qubits are not that those are the error prone and then very heavily sensitive. So it gets a lot of noise and then it will distort it. So what they do is now the physicists what they're doing is trying to combine multiple physical qubits into a logical group to get a proper calculations. So yeah, for example, if somebody wants to crack in a 24 hours to crack the 2048, it take 1.17 million physical qubit required with a high error rate. And then if you have a quantum computer which is have a low error rate, it can require only 0.34 million. And you may heard this story. Yeah, so this lot buzz around it after we presented in October 14th on in the ITF. The next day they did it, but what they did is they shown using the D wave advantage processor. They tried to find out the only the small factor of the 22-bit. So it's not immediate danger now. But anyway, let's see that's what are the companies are developing these quantum computers, and then see how in their roadmaps. So I can think of only the three. IBM and Google are doing good, and then they are actually have a very ambitious plans. When their roadmaps are different and unique, they are building in a different ways. Yeah. So currently, IBM have a 156 processor Heron 2, which I used in my demo. And but they have already the Condor they released, which is in 2024, I guess. And these are we can able to access via cloud few of them. And the Google have a 72 with the Sycamore. Maybe they have a very ambitious goal to reach 1 million qubit system by 2029. I don't know, really. It's very ambitious. Yeah, rest of other companies also building the quantum computers. They have a couple of other names. I didn't add it because no, its size was too big. So yeah. So, so what are the governments and an organization doing? So they already aware of this threat since 2000, maybe one or two. So, but the NIST was took it very seriously, and then they started doing the quantum resistant processing. So they started in 2016. They invited the quantum resistant algorithms across the world from the brightest minds, and they got 82 submissions. Out of this 82, they shortlisted in 69, and then they had a couple of rigorous round. Finally, on 13th August 2024, they released these four. So we can use it. These already finalized. And they also added few more for the alternative. So these are not yet finalized. Maybe by end of this year, they can get it something. They are still in progress. So we got till now here, we understood a lot of concepts and a lot of stuff. So how we can do the crypto at quantum level? We have a couple of options here. We can do in a three ways mainly. There are other ways as well, but these are the main ways. If you want purely quantum level systems, you can have it a QKD, which is the quantum queue distribution. These are the protocols, very old protocols. The BB8 4 protocol was introduced in 1970s or 80s, I guess, if I'm not wrong. And then E91 was introduced in 1991. These are a couple of companies are providing, but I don't know the reliability of these devices, but they are still doing it. We have a second option is the PQC, which we discussed in the previous slide, was this recently introduced. But the most interesting part is we can't directly transition to the post-quantum cryptography because our customer might not be having access to that, and all the products doesn't have a PQC. So the best option we have today is the hybrid cryptographic models. Okay, so we will going to discuss in a like why and the how helpful it is. So there is a document released by NIST. It was a wonderful document. If anyone wants to have a look into it, please scan it, and you can directly get a download link of the copy. It was released on November 2024, just recently, and it's given very detailed transition to the post quantum cryptography. And please don't afraid, it is not efficiently guided. Next one. So why we need a hybrid key exchangers? Because it's a practical and practical integrations, and it also enhance our security, and the transitional security is there, and then it will be a future proofing. At the same time, if someone, or maybe if we, in a next year or next or 2 years, maybe the compliances like a NZISM or maybe PCC or HIPAA can be introduced, you should comply with the PQCs, then it will be useful for us as well. So we just see this, anyone is adapted this now. So these are the early adapters. A couple of products and services already included the PQCs. If the main one is Apple, one they recently introduced, and they're already using the signal by last 2 years. These are the protocol names they have used in that. And then, yeah, these are the mix of with the classical encryptions which we're using today and with the PQCs. And they have a IBM systems also they released with the mainframe, and the browser by default they are using the enabled by default the supporting the PQCs. And this particular company was saying that offering the key distributions, but I'm not a salesperson of that, but I just added just to be fair. And one more thing is that DGCert is also interestingly giving the certificates. So you can create a certificate and we can try in your testing environment. We are trying actually in our company. And Microsoft also introduced the PQC algorithms in their main library just 4 or 5 days back, I guess. If any bug bounty hunter, you can start digging that. They change the code. And they have many more examples, but just to get a point. Yeah, if someone, if it's already implemented, how can I check? It's very simple. We are all hackers here, so mostly you can check a TLS version. If it is TLS 1.3, most probably it is already supporting the PQCs. And then check the cipher. I'll show you some examples. So if you can look at these one, so they can say that if you go to this website, they correctly say this if you are quantum post-quantum secured or not. And then if you really wanted to check in other website, which is like a already implemented, you can go to the developer tool and then check the key security. You can find whether it is supported or not. Maybe connection there or not, it would be a different story, but you can at least see that whether they are included in the certificate or not. Yeah. So finally, in conclusion, I will just take you through the couple of takeaways, and then I will answer the first question, which is should we afraid or not? First one is the quantum system poses real threat to our current public key infrastructure, not all. However, yeah. However, and then the quantum resistant standards are existed, but it may take time to adapt every single product which we use, even the IoT and then all other stuff. Third one, transition to quantum resistant cryptography is a complex, but we might not have a choice if you have a compliance and other stuff for many of the company, not all, but many. Finally, I can say the major players like I can say major players or suppliers already introducing PQC into their systems. So we can keep an eye on them actually, and then we have to start implementing our. So next one is that. Yeah, so we have to start now to preparing for the better safe, better than the quantum broken. So final one, I can say that this is the wonderful piece of document. I took it from the Taiwan one. It is like we have to prepare, prioritize, remediate. So we have to collect all our. We have to look the landscape of our infrastructure and then see where it is important, critical sites, and then sites or maybe devices, and then we have to be prioritized when to do what, and then we have to remediate. So as I mentioned, we already have a DGCET is providing the certificates, so you can happy to use it. And if you feel that it's maybe urgent one, you can try in here test and the test environment. It will be very helpful. And then you can talk to the DGCET guys; they are very quite helpful. So yeah, thank you so much for your attention. It has been great to present the CHCon at first time as a both attendee and speaker. I hope I have helped clear up some of the thoughts and mystery sign around the quantum cryptography. Yep, thank you so much.
I am a super genius.